Hey everyone, welcome to part 2 of chapter 8. We're going to continue talking about hypothesis testing and get a bit more specific about the different steps involved in hypothesis testing. So let's actually see how we would set up hypotheses and test them throughout a series of 5 steps. First, we're going to state the research question that we have and make hypotheses. Then we'll set a decision criterion. We'll collect sample data, calculate statistics, and finally make a decision about whether that hypothesis is supported or not supported. So first up, let's talk about stating research questions and turning research questions into hypotheses. So in research, we actually make hypotheses about populations. We don't make them about the single sample that we pull from the population. We want to make a hypothesis about a population, and then we're trying to get at or infer things about the population from our sample. That's why it's called inferential statistics, what we're about to cover. So we have two different kinds of hypotheses. One is called the alternative hypothesis. Sometimes, and your book mentions this, is called the scientific hypothesis, but we'll call it the alternative hypothesis, which is denoted by H1. This is the hypothesis that there actually is some kind of effect. There's some kind of relationship. There's some kind of difference between two potential groups, depending on how your data is set up and what kinds of questions you're looking at. The null hypothesis is the opposite of that, denoted by H subscript 0. This is the hypothesis that there is no effect of, let's say, drug A on your population, or there's no relationship between two variables, or that the two means of two different groups are not significantly different. So the null hypothesis is always saying there's nothing going on here. The alternative hypothesis is saying I think that these groups are different, or I think that my intervention has somehow made readers be able to read much faster than people who didn't do this, or whatever. So typically in research, we start with a question that is interesting to us as researchers, right? So does memory change with age? Or can you treat depression with antidepressive medications? Or can you increase IQ by using some kind of teaching intervention? All right. Well, you need to drill down a little bit further to make explicitly testable hypotheses. Okay, we start with the alternative hypothesis, which again is the hypothesis that you think something is happening in the real world. You think that some kind of effect is present. Then the null hypothesis is saying, no, I don't think there's actually an effect actually happening. All right. So in this case, if we're thinking about does memory change with age as the research question, the alternative hypothesis might be in the general population, memory abilities do change with age. That is a directly testable statement. The null hypothesis is in the general population, memory abilities do not change with age, right? That's just sort of saying, I don't think there's really anything going on. Now, this is a really important distinction. Hypotheses can be stated one of two different kinds of ways. You can have what are called two-tailed hypotheses, or you can have one-tailed hypotheses. Two-tailed hypotheses are basically called that because they're bidirectional, and I'll show you that on a distribution in a minute. But what you're saying is, for example, in the general population, memory abilities change with age, but you don't commit to a specific direction. So two-tailed hypotheses are basically like non-directional hypotheses. You just think that there is going to be some difference or some change between two different groups, or before and after some kind of experimental manipulation that you do. A one-tailed hypothesis is directional. So you actually have to commit to saying, like, in general, older individuals have lower memory scores than young individuals. Not just that they're different, but in fact that older people have worse memory scores than younger individuals. So that actually gives a direction. It'd be the same thing. Another example would be like if you think drug A will change a group's depression scores compared to the control group, that's two-tailed, that's non-directional. But if you will think it will decrease depression scores in your experimental group, that's one-tailed because it is directional. And I want to talk a little bit more about the kind of language we use in hypotheses. So sometimes you'll see people talking about effects, whether there are effects of a certain thing or not. And other times you'll see people talking about whether means, like averages of two groups, are similar or not. And there's overlap here, like you can be talking about the same thing. So for instance, if I'm talking about effects, maybe my alternative hypothesis, H1, there is a significant effect of drug A on depression. And so what I would be expecting here is, if we're talking about means, the mean depression score of the people who took drug A in the experimental group is significantly less than the mean depression score of people who did not take drug A, which would be the control group, right? So these are saying the same thing. There's a significant effect of drug A on depression. Translating that into means would say the average depression scores of people who take this drug should be less than the average depression scores of people who don't take the drug. Now, you can see even further that you can represent this mathematically using symbols. For example, the population mean. Again, we're talking about when we're in hypothesis testing and creating hypotheses, we're talking about populations. So that would be mu1, that is the average depression score of the first population, which we'll say is people who actually took the drug. The average depression score is less than the average depression score of mu2, that's population 2. That's people who didn't take the drug, so that's the control group. Now that's if you have a one-tailed hypothesis, meaning you have a directional hypothesis. I actually think that that this drug A will decrease depression scores. If you use a two-tailed hypothesis, meaning non-directional hypothesis, you would just say, I think people who take drug A will have a significantly different average depression score. You're just being non-committal about it. You're not saying, which direction it might be. You can also represent that mathematically using mu1 for the average depression score of population 1 is just not equal to, that's the equal sign with a slash through it, not equal to the average depression scores of population 2, which is the control group. Okay, hopefully that makes sense. Let me know if you have any questions about that for sure. Okay, so the previous slide was about the alternative hypothesis. What about the null hypothesis, H subscript 0, so H0? That would be there's no significant effect of drug A on depression. That would be for a two-tailed hypothesis. For a one-tailed hypothesis, you would say there's no significant effect of drug A on depression, or drug A actually worsens depression, meaning drug A, depression scores for the group that receives drug A will actually be higher than the average depression scores of people who don't receive it, right? So we're just flipping it, making it the opposite of the alternative hypothesis. And then you can see that if you're talking about means, how that looks, and mathematically, what you're saying is that I think the average depression scores of the two different groups, even after one of them has taken the pill, will not be different at all. That would be in the case of a two-tailed hypothesis. So you would say mu1 is the same as, equals mu2, meaning the average depression scores for both of those groups, they're not different at all, meaning that the pill didn't work, it didn't have any effect. It could also be the fact that you think that for a one-tailed hypothesis, well, actually, depression scores increase or stay the same. The depression scores increase or do not change, basically. That would be for a one-tailed hypothesis, and so you could do mu1, which is the experimental group. The average depression scores for the experimental group are actually greater than or equivalent to the depression scores of the control group. Hopefully that all makes sense. Now, this example is about something going down, like depression scores actually decreasing. But oftentimes when we're talking about averages, we're also interested in things increasing. So for example, if I'm trying to conduct a study where I'm trying to do a particular type of teaching style that actually increases final grades of a particular class, and I compare that to a group of students that I don't do anything differently for. Well, then my alternative hypothesis is that the particular teaching style that I take on in the experimental group will increase the average test scores of that group compared to students who I don't do that for. And so you would basically be flipping the signs. And so you have to be the signs of greater than or less than. So you got to be careful using your mathematical symbols depending on what your hypothesis actually is. And so this is really important. This is hypothesis testing logic. This is how we think about in all of the social sciences, how we think about what we're doing when we perform an experiment or a study. First of all, we're assuming that the null hypothesis is actually true. We assume that there really is no effect, let's say, of drug A on depression, or no effect of an intervention on people's reading ability, or there's no mean difference between two different groups of people. Now, we can't actually know this because the null hypothesis is saying that there is no effect. That would mean that like we'd have to observe every single instance of whatever thing we're interested in that has ever happened or will ever happen in the population, and there's just no possible way to do this. But we're using a logical trick here, that we are first assuming that the null hypothesis is true. Then, after we collect data and we calculate these test statistics, which we'll do in a bit, we look at, well, what is the sheer likelihood of finding let's say an average depression score this low or even lower if we assumed that there actually is no effect of drug A? Or we could say that a slightly different way using a different example. Okay, after collecting data on whether a certain teaching intervention helps people read faster, once we find the average of the people that actually took the intervention and went through some program to help them read better, we find that mean and we compare it to the mean of people who didn't go through that program, and we say, okay, well, what's the sheer probability that people can read this much faster if we assumed there actually was no effect of that intervention? What's the sheer probability, the chance that that would happen randomly? Because if the probability is actually really small, like it's not likely at all that we would see people read this fast if the intervention actually didn't have any effect, then we can usually reject the null hypothesis and conclude that our alternative hypothesis is correct. So this is the dirty little secret of psychological research, and in fact, most research from any field that uses hypothesis testing, okay, is that we don't ever actually prove the alternative hypothesis is true. We never prove it. All we've done is a logical trick that says, well, we found evidence that the null hypothesis is not true. So what else could it mean? That means that, oh, well, I guess if the null hypothesis is not true, that means the alternative hypothesis is probably true. Well, we didn't actually show anything to prove or to make true the alternative hypothesis. All we've simply done is tried to show evidence that suggests that the null hypothesis is not true, should be rejected. So it's a bit of a logical trick, and that's why research studies don't ever prove anything to be true. They basically just provide supportive evidence for something, but you don't ever actually prove that your hypothesis, your alternative hypothesis, is true. Also, a little bit about wording, like when you're writing up a results section. Even if you fail to reject the null hypothesis, meaning that, well, it is actually likely that we would see depression scores like this if the drug A did not work. And so it's like, okay, well, then we don't have enough evidence to reject the null. So what happens, though, when you're writing these results, we don't actually conclude that the null is true. We have just not found evidence to reject it, because we would need to conduct many, 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 many more studies to see whether these results and this pattern of results actually continues to be the case or not. So we can't actually say the null hypothesis is ever true. Nobody knows in all reality if the null hypothesis is like capital T, the truth of the world, because you'd have to do an infinite number of studies to see if that were true. But if we have a study that shows us that we can reject the null hypothesis, then we do assume that the alternative hypothesis is true. You don't say the same thing for null hypotheses. You don't ever like say in a result section, the null hypothesis is true. You just say, we fail to reject the null hypothesis. I know that was a lot. So let's move on to the next step, which is setting a decision criterion. So after you make hypotheses, what you need to do is decide, well, how will I know if those hypotheses, turn out to be the case or not? Like, what would actually look like evidence for or against a hypothesis? And so this is where we're setting a criterion for our decision making for step 5. So we need to figure out, well, how extreme does, let's say, a sample mean have to be in order for it to be considered evidence that the alternative hypothesis is true and that the null hypothesis is probably not true? How extreme, how unlikely does this mean or whatever that we're measuring have to be? And the way that we decide that is by using what's called a decision criterion, also known more commonly as the alpha level, which is represented by the Greek letter alpha level. This is a probability level used by researchers that sets the cutoff that allows them to reject the null hypothesis, okay? Usually in psychology, we set this to 0.05, and that is going to help us demarcate on the null distribution, the comparison distribution, where we can set up what's called a critical region, where basically if we find a value like a mean, a sample mean, that is within that critical region, meaning it's extreme, it's in this extreme region of the distribution, then we can reject the null hypothesis. If it falls outside of that region, we fail to reject the null hypothesis. So we set the alpha level in this class and in basically all of psychology to 0.05, meaning a 5% probability. 5% what? Well, 5% chance or 5% probability or 5% likelihood that the sample mean that we calculated, actually comes from this distribution. And so we typically in social sciences or in psychology set this criterion, this decision criterion, this alpha level to 0.05, which is 5%, which means if our sample mean has only a 5% chance or lower probability of actually being found within a distribution of sample means, then that's really unlikely. that it actually even comes from this distribution, and therefore it is statistically significantly different from the distribution of sample mean, or different from the other group that we're comparing it to, and therefore we will have rejected the null hypothesis. And so in other words, what this is saying, right, is that if the sample mean that we are obtaining only has a 5% chance to even be found on this distribution, the null distribution, then it's probably from a different distribution, because it'd be incredibly unlikely that we would find such an extreme value for the mean, if in fact the null hypothesis was true, if in fact there really was no relationship between the two variables or no difference between two means or something like that. So again, we're trying to set up a critical region, and if our sample mean or sample z-score or whatever it is we're looking for falls within this critical region, we reject the null hypothesis. Okay, well, if you were to look up in a unit normal table, hey, what is the z-score cutoff for 5% or less of my entire distribution? You would find a z-score of 1.64, meaning 1.64 standard deviations above the mean. If we find a mean or a z-score that is at least 1.64 standard deviations above the original distribution's mean, or the sample of mean, then we can be pretty confident that the sample actually comes from a completely different distribution. It wouldn't even be on here because it's so unlikely that we would actually find a mean that high or that low if you're looking at something decreasing, like in the drug A decreasing depression scores. So if we find a z-score that's above 1.64, then boom, we reject the null. If we find a z-score that is below 1.64, then we don't have enough evidence to reject the null. Now, what if you have a two-tailed hypothesis? Well, then you have to take the critical region, which was 5% or 0.05, you divide it by 2 because you have to have half on the lower region of the distribution and half on the upper region of the distribution. So that actually cuts the alpha level basically from 0.05 into 0.025, because that's half of 0.05, right? And then you go into the unit normal table and you look up, well, what's the value that I would find in the tails that would give me a 2.5% or a 0.025 probability of finding the mean or the z-score in that critical region. You would find a z-score of 1.96. So if there's a z-score or a mean that falls above 1.96 standard deviations from the mean or below 1.96 standard deviations from the mean, that means that that sample does not probably come from this distribution, and we reject the null. And this diagram is just showing you a comparison between where the critical region cutoffs are for a two-tailed versus a one-tailed hypothesis. And you can see that the critical region for a one-tailed significance test of 1.64 includes more of the distribution on the right side, right? So that means that there's actually a higher likelihood that you'll reject the null hypothesis because it's more likely that you're going to find a mean or a z-score within that larger region on the right-hand side. Of course, that's negating the left-hand portion, but a lot of people don't like using one-tailed hypotheses in research because it actually it makes it easier to find significant results. So we typically use two-tailed, but for the purposes of this course, either one works for sure. So we just set our level of significance or our decision criterion, which is represented by alpha, and we always set it in this class to 0.05 or 0.050. Those are the same thing. And so basically that's saying, hey, awesome. We know that the cutoff is 0.05. If we have a mean that falls within the critical region representing 5% or less likelihood, then we can reject the null and conclude that it is actually statistically different or higher than whatever mean we're comparing it to, or z-score or something like that. So that's just the criterion. We haven't actually collected data. We haven't actually calculated any statistics. So we would next move on to actually collecting sample data. So then we would move on to actually using one of those sampling methods we talked about towards the beginning of the semester to recruit a sample, have them participate in our study, and we collect measures of interest, so whatever variables that we want during their participation. And then finally, we can move on to actually calculating inferential statistics. So let's see what kinds of inferential statistics we are calculating to actually be able to test these hypotheses that we've made. Well, how do I know which test to actually use? There's a ton of different kinds of statistical tests, and they create different kinds of inferential statistics. Well, it all depends on the nature of your data and the types of hypotheses and research questions that you're actually asking. In our case, we're going to be calculating the test statistic for a one sample z-test, which you can see all the way kind of on the left-hand side. If we have one sample and we're comparing it to a previously known population distribution, or really it's the distribution of means distribution, and if we know the population standard deviation, then we're going to be using this one sample z-test. So let's see what that actually looks like. This is a super helpful flowchart, and you'll want to keep it handy for the rest of the class because it'll help us understand when and why are we using certain statistical analyses. So in a one sample z-test, you've got to know a number of pieces of information. You've got to know the population standard deviation. You've got to know the sample size that you have taken, and that'll allow you to calculate the standard error. So we've seen this slide before. The standard error is basically the standard deviation of the distribution of sample means, and it represents an estimate of sampling error. So let's take the example from your book where a teacher has recently implemented online quizzes in the hopes that that would increase final exam grades for their most recent course. So we would be comparing the average final exam grade of students in this class, which is our sample, comparing that to the entire population distribution of previous classes' final grade averages, and those classes in the past didn't have access to these online quizzes. So if we set up a null hypothesis, it's that the online quizzes didn't have an effect on the average final exam scores, meaning that the mean final exam score for our sample would not be significantly different or would be equivalent to the mean of that distribution of classes that came before it that didn't have online quizzes, or that in fact that the final exam is less than, because remember with null hypotheses for one-tailed hypotheses, we have to include both of these things. The alternative hypothesis is that the online quizzes actually did help, and so the mean final exam grade for our sample is going to be higher than the mean final exam grade of that distribution of classes that came before. All right, so this is our first inferential statistic. Woo! We are calculating a z-statistic, which is basically identical to z-scores. We've already been calculating z-scores, but in this case, you'll see that the denominator is a little different, just a little different. That's because we're no longer talking about just a distribution of raw scores and converting that distribution of raw scores into a distribution of z-scores. Now we're talking about z-scores on the distribution of sample means. So that is z subscript x bar. That's telling you this is a z statistic that's going to be found on the distribution of sample means. Okay. And that is equal to, you need to know a number of pieces of information here. The sample mean, x bar, minus the population mean, mu, divided by this bottom segment, right, the denominator, that is standard error. That's the calculation for standard error. So that is sigma, which is population standard deviation, divided by the square root of n, the sample size. Well, we've got all those pieces of information here. So the average final exam score for our sample was 82. That's pretty dang good. That's high, right? You subtract that, you subtract 75 from that. 75 is the population mean. That is the average final exam score for all the classes who took, who did not have online quizzes. All right? You divide that by the standard error. Remember that the standard error is the standard deviation of the distribution of sample means. So this really is the same thing as calculating a regular z-score, except for the standard deviation is now the standard error, and it involves kind of one more piece of information, which is the square root of sample size. So 82 minus 75 divided by, we know that the population standard deviation in this case is 3. We had 30 people, so 3 divided by the square root of 30. Finally, you get a z value, a z statistic. This is a real inferential test here of 12.73. Now that's huge. That's still 12.73 standard deviations above the mean, but now it's 12.73 standard errors above the mean, because the standard deviation of the distribution of sample means is standard error. So this is 12.73 standard errors above the mean. That is an incredibly high amount of standard deviations above the mean, right? Like in the book, it doesn't even go that high, for sure. This means that the likelihood of seeing such a high sample exam final grade, the likelihood of that is going to be almost zero. It's like 0.0000000001 or something. You know what I mean? It's astronomically small. I guess I should say microscopically small. You would never expect to see such a high value for the sample mean if the null hypothesis was true. If online quizzes really did nothing to help raise final exam scores, you would never expect to see such a high average of 82. And we know that because we work out the z number, we look it up in the table, we try to find what the probability is. The probability is tiny. It's almost nothing that you would ever find such a high or such an extreme score if, in fact, the null hypothesis was true. So finally, we need to make a decision about how that test statistic relates to our hypothesis. Okay, so the probability of observing a z statistic of greater than or equal to 12.73 is basically zero. Like it's, the probability of that is, the table doesn't even go up that high, because it's like there's no chance you would ever see that if the null hypothesis was true. And so what we've actually just found by looking up in the standard normal table, or the unit normal table, or the z table, it's got a bunch of different names. We've actually just found something called a p-value, and we've been doing that all semester, but I haven't been calling them p-values. But it's the probability of getting a specific result in inferential terms, we have many different inferential test statistics, a z-value, a t-value, an f-value. Correlations are like r values, basically. The probability of getting a result as extreme or more extreme if, in fact, the null hypothesis was true. So remember that the probability of observing such a high final grade, average final grade on the exam, is basically zero. If the null hypothesis was true, and the null is that the online quizzes didn't help at all to increase final grades. So if the null was true, and in the real world, even though we could never know it, even if in the real world, if the online quizzes really didn't help anybody, well then, maybe we just observed our finding of 12.73 standard deviations above the mean by total random pure chance. Just by random chance. Just happened to be that day everybody was on it and they did really well on the final. Okay. Well, what's the likelihood of that happening, of just observing it by chance if in fact online quizzes didn't help anybody? The probability was zero. There's no chance that it didn't help. So that means that we can reject that null hypothesis and conclude that the alternative hypothesis is true. The alternative hypothesis being that online quizzes did improve average final grade. Okay, a small p-value of less than 0.05. Remember 0.050, that's our cutoff. That's our alpha level. And so the value that we just found, which is way smaller than 0.050, it's 0.000. A very small p-value of less than 0.05 indicates there's a very small chance of getting that test score that you calculated if in fact the null was true. And so therefore we reject the null and conclude the alternative hypothesis is true. The p-value of less than 0.05 means there's less than a 5% chance that we would ever see such an extreme score if the null was true. So we reject the null. Now a p-value of higher than 0.05 means that it's actually somewhat likely we would see that kind of result if the null hypothesis was true. There's a more than a 5% chance that we would see that. So we fail to reject the null if the p-value that we look up in the table or that we calculate is higher than 0.05. We fail to reject the null. This slide just states everything I basically just said out loud, but this is good for you to come back and look at. It's basically just saying we compare our p-value to the cutoff value. It's way lower than the cutoff value, which means we would not really expect to see a final exam score of 82 or higher. It would only show up, well, it would show up never. It would show up 0% of the time if the null hypothesis were true. So it's very unlikely that anybody would ever see such a high score if online quizzes didn't help anybody. So we reject the null hypothesis and conclude that in fact online quizzes did help people and that our population, our sample, is from a different population than all of the students who came before. And which population is that? Our students are the population who have online quizzes. The other population did not have online quizzes. In statistics and research, you often hear the term significance testing. So far what we've done is like calculated a z-value, or in the future a t-value or f-value, and then we look up in a table, well, how likely is it that I would ever see such a high value or just such a value? And that p-value would be in the table itself. But when you use SPSS or some kind of statistical software, it gives you the p-value. It'll actually calculate a p-value for you and spit that out on the output, so you don't have to look it up in a table. That is called the significance test. It gives you the p-value, and the p-value then you compare to alpha level. If the p-value again is less than or equal to alpha, which we always set to 0.05 in this course, you can reject the null hypothesis because it means it would be very, very unlikely you'd ever see a z-score that high or a z-score that low or a t-score that high or a t-score that low if the null is true. So we reject the null hypothesis and conclude that the alternative hypothesis is true, or at least that we found support for it. So a statistical inferential test, such as a t-score, z-score, that kind of stuff, is significant. We can say it's significant if the p-value is less than or equal to 0.05. But an important caveat here is even if a statistical test is found to be significant, so like the two means of two different groups, average depression scores, are significantly different. So the p-value for that test was equal to or less than 0.050. It doesn't necessarily mean that that finding is important. So there's a sort of a difference between importance or meaningfulness and statistical significance. You could find a statistically significant difference between two things, but it doesn't mean that they're necessarily like that's a really important difference. And it is really the p-value is oftentimes dependent on the sample size. And if you have a really high sample size of like 50,000 people, then like almost any difference between two means will become statistically significant, but it doesn't mean that they're actually really in the real world very different from each other. So you could say, drug A versus the placebo, on a scale of 1 to 9, people who received drug A had a mean depression score of like 4.5. The control group, on the other hand, who didn't receive the drug, had a mean depression score of 4.6. And it's like, well, 4.5 and 4.6 are not that different at all on a scale of 1 to 9. But if you had enough people in the study, it might say the statistical test that you do, which would probably be an independent t-test, which we'll talk about in the next couple of chapters, it might actually give you a significant p-value of less than or equal to 0.05. So it would be those two means, 4.5 and 4.6, would be statistically different, significantly different, but not necessarily meaningful in terms of like, well, those people aren't that much more or less depressed no matter which group they're in. So hopefully that kind of makes sense. So it's important to look at statistical significance, absolutely, and also think about, well, what's the real world significance of that too? All right, so let's talk about another very important concept when we're talking about hypothesis testing, and that's type 1 and type 2 errors, okay? So when we reject or fail to reject a hypothesis in our studies, well, in the real world, the null hypothesis could be true or false. And so we might actually accidentally make a mistake. And that's not through necessarily any fault of the researcher, but it could just come down to random chance. So let's walk through this idea using the example of, I think that, let's make the alternative hypothesis that wearing glasses makes you smarter. All right. Now, you'll see on the columns, the true and false columns, if the null hypothesis is ... true or false, we don't ever actually know the answer to that in the real world, because you'd have to go find every single human being that has glasses or doesn't have glasses. And really, you'd have to figure that out for every human being that ever was or ever will be. Okay, so we don't ever know in the real world if the null hypothesis is true or is false. All we know is the rows, whether our study says that we rejected the null hypothesis and concluded that yes, in fact, the alternative is true and wearing glasses makes you smarter, or we fail to reject the null hypothesis and so we retain it and the null hypothesis is supported, which means that, well, we didn't find enough evidence to suggest that wearing glasses makes you smarter. Again, we never think that we never like prove the null hypothesis true. We can either reject it or fail to reject it. Those are the only options. So what happens if we were to reject the null hypothesis and conclude that yes, glasses make you smarter, but actually in the real world, the null hypothesis is true, that wearing glasses doesn't make you smarter? Well, we've just committed what's called a type 1 error, or also known as a false positive. So you can see that's where the top left quadrant here. The null hypothesis in the real world, it's true, but we rejected it in our study. Oh no, that is an error. We made an error. That's a type 1 error. Again, we don't ever necessarily know if we've committed a type 1 error, but we know what the probability of making a type 1 error is, and that is our decision criterion. That's our alpha level. The probability that we make a type 1 error is 5%. Because if we reject something, because the probability of our test statistic, of obtaining the test statistic, was less than 5%, well, that could have happened just by random chance. It's unlikely, but it could have happened just by random chance. Okay. Now, if we reject the null hypothesis, and in the real world, the null hypothesis is false, that's a correct decision, right? Like, we rejected the null, and that's good because the null was false. So the alternative is true. That's the top right quadrant. The bottom left quadrant is we fail to reject the null. So we're going to say, well, we don't have enough evidence to suggest that wearing glasses make you smarter, so maybe wearing glasses doesn't make you any smarter. Well, if we don't reject the null, because it turns out that that's good because the null is true, then we also made a correct decision. We decided that no, there's no effect of glasses on intelligence. So we were correct. But it's also possible to make a type 2 error, which is that we fail to reject the null, meaning we found no significant differences, or we found no significant relationship between variables, when in fact, in reality, the null is false. The alternative is true. And wearing glasses really does make you smarter, but we didn't find that. We didn't reject the null, and we didn't accept the alternative. That's a type 2 error, and that's called a false negative. So it's a good thing to be aware of these. We can always be wrong, and we wouldn't necessarily know if we're wrong because it's basically impossible to actually discover what the real null hypothesis is, whether it's true or false in the real world. All right, here's a silly example. What is an example of a type 1 error for someone taking a pregnancy test? The answer is C. They say they are pregnant when they really are not. They say they are pregnant when they really are not. Right? So that would be saying something like, that's a type 1 error. That's when you say, yeah, there's really an effect here. There's really, the mean of my sample is much bigger than the mean of the distribution of sample means, and that's the comparison distribution, which is representing the null hypothesis. So I'm going to reject the null hypothesis and conclude that there really is something going on here. But, we just made an error. It turns out the null hypothesis was actually true, and you should not have rejected it. All right, thanks for sticking with me to the end here. So you got a twofer today. You get 2 memes for the price of 1. On the left here is all of these Spider-Men are saying the same thing, and this can be kind of confusing sometimes for students who are exposed to p-values for the first time. All of these are the exact same. So a p-value of equal to or less than 0.05 means that there is something statistically significant happening. Either there's a statistically significant relationship or a statistically significant difference between 2 means or something like that. You're also, when you get a p-value of less than or equal to 0.05, you reject the null hypothesis and conclude that the alternative hypothesis is true. And all these things are the same thing because if you reject the null and conclude that the alternative is true, the alternative hypothesis is that there's going to be a statistically significant difference between 2 means, for example, or there is going to be statistically significant effects of some kind of intervention on some kind of outcome of interest. All right, so all those are the same. And the meme on the right, this is what p less than 0.05 feels like. It feels awesome. Why? Because most of the time in psychology, we're trying to do some kind of experimental manipulation, or we're trying to use some kind of education program or some kind of drug or some kind of intervention that helps people in some way. And so what we want to do is we compare this experimental group to the mean of the experimental group, their depression scores or their I don't know, their ability to get better grades or their reading scores or their standardized testing scores or anything, right? We want to compare that to the control group who we've essentially done nothing to, and we want to see that those means are significantly different because it means that whatever our intervention is, it's working, it's doing something. And so you want to see significant p-values of less than or equal to 0.05. So anyways, we'll talk more about that throughout the rest of the semester, but I hope you have an excellent rest of the day. Let me know if you have any questions. I know this one was, yeah, quite a lot. So I'll see you in the next video.